Welcome everyone to the online corridor, or the, how should I say, the electronic room that we have. And we very much hope, as we were just discussing, that after the spring semester, things will get closer to normal when most people will get vaccinated. And for the time being, we are not going back to the building, and also the annual conference in May will definitely not take place in person. But we have to decide whether to hold an in-person conference in December, or keep an online conference in May. That's something to be decided in a month or two. So without further ado, Achilles.
Yes, so hello everyone, welcome. Indeed, this is the first colloquium of the semester. So we're very happy to have Antony Speranza with us today. So Antony has received his PhD in 2018 from University of Maryland under Ted Jacobson, and he's been a postdoc since at Perimeter Institute. So he's interested in gravitational physics broadly. He's done work on entanglement entropy and edge modes, etc. And today he's going to tell us about black hole entropy, symmetries, and observables. Take it away, Antony.
Okay, thanks. Thanks a lot for the opportunity to talk to you guys today. So yeah, I'm going to be talking on some work that's contained in these 3 papers that I put out last year. And it kind of goes under the general idea of symmetries and observables for localized subregions in gravity. So is this, can you see this?
We see your first slide.
Sorry about this. My iPad just stopped screen sharing. I'm gonna have to reconnect it. Let's see. After 0. Let's see. And do you know if the screen sharing is available? Let me just try it. Okay. Okay, sorry. I'm not sure what happened there, but okay. Now we can see the second slide, that's good. Okay, as I mentioned, I'm interested in this idea of observables in general relativity. And it sort of, the whole thing starts with this observation that observables in general relativity tend to localize to asymptotic boundaries in your theory. So it's well known, things like the ADM mass, the Bondi mass, or more recent work on BMS charges in observables are all defined at asymptotic infinity. And the reason this happens is you can show that it follows from the diffeomorphism invariance of the theory. And it's also kind of a major motivation behind why holography and things like ADS-CFT actually works in a quantum theory of gravity. So the thing I'm interested though in is a more localized notion of observables in general relativity. So these would go under the name of quasi-local observables. And the idea is if you had some sort of finite subregion inside of your space-time, is there a sensible notion of observables, things like the energy density inside that subregion? So this could be relevant for things in astrophysics where you're not always sitting all the way out in infinity. You can measure things like the moments of the Earth's gravitational field with satellites that are not too far away from the Earth. and so characterizing local notions of energy in the real world. But the other reason I find it interesting is these charges associated with finite subregions kind of have relevance for the quantum theory as well. So in general, what happens is when you introduce a boundary, you can think of the boundary as breaking some of this diffeomorphism invariance of the theory, and you can associate charges with these broken diffeomorphisms. So related to why these are interested in the quantum theory, one thing that you can use these charges for is defining entanglement entropy in gravity. There's this observation that in general relativity or quantum GR that the Hilbert space doesn't factorize into a spatial subregion and its complement because you have constraints that basically relate observables in one subregion to those in the other. And sort of a more pedestrian way of thinking about this is this also occurs in something like a gauge theory, where you have like Wilson loop observables that aren't really associated with one subregion or the other. And so that prevents your Hilbert space from factorizing. But what you can do is you can introduce charges that kind of end at your boundary in order to force your Hilbert space to factorize. And these are these boundary charges that we're talking about. And in general, this is relevant for entanglement entropy and gravity, because when you're constructing the global Hilbert space from these localized ones, you generally end up entangling these boundary charges, and that gives you important contributions to entanglement entropy. This problem of factorization is also interesting in its application to recent discussions of the page curve for black hole evaporation, where it's important to be able to separate your gravitational system into sort of the bulk and a factor associated with the radiation. So there could be some interesting applications to these black hole evaporation discussions. Sort of related to this problem of entanglement entropy and factorization is the more general concept of black hole entropy. So we've known since the 70s that the black holes possess an entropy that's proportional to their area. And if you're interested in some microscopic description of that entropy, that should, be controlled in some way or have a description in terms of the charges that you find living at the boundaries. In particular, if you can find a conformal algebra, something like 2 copies of Virasoro acting near the boundary, so near the black hole horizon, you would say it's kind of natural to associate a CFT with this boundary theory. And the remarkable thing is, just making this observation, you can, in many cases, apply this Carty formula, which tells you what the density of states are in a CFT. And you can apply that using some central charges that you computed in the gravitational theory, and you end up matching the black hole entropy. So this is some work that was first done by Andy, and then it's been followed up by, generalized to various types of horizons by Carlip and various other people. And I'd like to point out specifically this paper by Hako, Hawking, Perry, and Strominger from 2018, which was kind of a major motivation for some of the things I've thought about with this, where you can really find these 2 copies of Virasoro and get a description of the black hole entropy there. So these sort of reasoning sort of motivates sort of generalizations of holography to, finite boundaries or something more localized boundaries like a black hole horizon. Okay, so the general plan is to kind of describe how exactly you define these quasi-local charges in gravity. And the technical tool was sort of developed by Walt Zupas, and I'll describe a few formal developments that I've worked on to sort of make the process better defined. And then I'll describe how you can define these Virasoro symmetries acting in the near horizon region, and how that relates to the black hole entropy. And time permitting, I might also mention some additional set of charges that you can define near more generic horizons and some interesting observables that you derive by looking at these symmetry algebras. Okay, so the idea for quasi-local energy is sort of, it's a concept that you can define even in ordinary field theories. And so in an ordinary field theory, you consider like you have some subregion sort of with a spatial slice that you call sigma, and you want to associate some energy density to that subregion. So in this case, it's familiar what you do. You just integrate the stress tensor over this subregion, kind of weighted by whatever translation you're constructing the charge for. And you can relate this stress tensor to the Noether current for this symmetry transformation generated by C. And you can show that the stress tensor kind of determines your Noether current up to, you know, exact terms. And the reason you can associate this with an energy is that you can use some sort of Hamiltonian formalism to show that this is, in fact, the energy that generates this translation along C in your gravitational system, or sorry, just in your theory. So you can show that the Hamiltonian is just given by the integral of this Noether current up to a possible boundary contribution. And so we see that the Hamiltonian and the quasi-local energy are equal in this setup up to these boundary terms. So this quantity L that you defined at the boundary is determined by the types of boundary conditions that you're imposing. And you know, different choices of L will lead to different boundary conditions, and also those boundary conditions give you a different notion of energy. So just as an example, if you do your usual scalar field, massless scalar, the stress tensor is given by this familiar formula. This Q contribution is just identically 0. And depending on the type of boundary conditions you want to impose, so say Dirichlet, you simply don't have to add any boundary contribution to the Hamiltonian, and the energy is just given by the integral of the stress tensor. But if, say, you were interested in something like Neumann boundary conditions, you would get an additional contribution at the boundary. So it's interesting to ask what's different about this construction in gravity. The main difference is that the stress tensor in gravity just vanishes on shell. So this local contribution coming from this bulk integral here is just 0 in gravity. And this is sort of the special feature of gravity, is that the stress tensor is 0. And you can just think of that as imposing the Einstein equations. So in this case, the energy that's captured by the Noether current is just a pure boundary term. And so this is why everything localizes to the boundary in a gravitational theory. And you still have this fact that different choices of boundary conditions will produce different notions of quasi-local energy. And one of the interesting facts that's been noticed, you know, for a while in gravity is that the choice corresponding to a Dirichlet boundary condition, where you want to fix the metric at the boundary, requires a non-trivial boundary term. So for time-like boundaries, this is the famous Gibbons-Hawking-York boundary term. So the reason for highlighting this difference is that this choice of boundary condition ends up being sort of crucial when you start applying this construction to charges on a black hole horizon, and in particular, if you want to go through and do this Carty formula for the microstates. This choice of boundary condition ends up being crucial, but it's not any different from understanding boundary conditions in an ordinary field theory. So for gravity, the interesting thing is that all of the energy is a boundary term, whereas this choice of boundary term, while important, is something that's not just localized to gravitational theories. So in order to do this construction more explicitly in gravity, generally the formalism that you use is this covariant phase space. maybe I can just go quickly through the ideas here. Is essentially you want to construct a Hamiltonian description of gravity. And sort of the central player in this whole construction is this symplectic potential, which we call theta. And it's just the boundary term that you get when you vary the Einstein-Hilbert action. So this is the thing you use to construct things like the symplectic form and construct the whole phase space. And you also use it to construct these Noether currents and Noether charges associated with diffeomorphisms. So the idea is if you want to construct a charge associated with a boundary, so let's say we have some subregion characterized by U, this blue surface will be like a Cauchy surface for your subregion. And we know that the charge is localized to the boundary of the Cauchy surface right here. And we're looking for some notion of energy associated with translation along this yellow vector C. So in order to do that, you need to decompose theta into a total variation piece, which is related to the boundary term in the action. A corner piece, which isn't super important for now, but it's sort of interesting additional contributions to the energy, and an additional term, which is the flux. So the flux is the thing that you want to set to 0 by a boundary condition. And so this decomposition just comes from the variational principle for a subregion. So if you have a Lagrangian, so the action is the integral of the Lagrangian plus this boundary term here. And when you vary this quantity, you get bulk equations of motion plus a flux through the boundary, which you set to 0 by boundary conditions. Or more generally, if you don't want to impose boundary conditions, you still use this flux to sort of glue and match subregions together. And so the nice thing is that once you've done this decomposition, you can give an explicit formula for the quasi-local charge. So this is a notion of energy for this subregion U. And it's given, so it depends on this boundary term here. So really the only thing you have to determine in order to make this procedure well-defined is what form the flux should be. And so something we've been arguing for is that the most natural notion of this flux is that it should take the form of a Dirichlet condition. So here I'm displaying the flux for, say, a null surface where the Dirichlet condition means it only involves variations of intrinsic quantities and so these pi's are something like the extrinsic quantities. So once you've fixed the flux to be of this form, it sort of removes any ambiguities in the construction and you can have well-defined charges. So there's some arguments for why you would use this Dirichlet condition. It gives you sort of an interesting interpretation of these pi ij's as this Brown-York stress tensor, and indeed this whole concept of quasi-local charges was sort of developed by Brown and York, and it gives a nice notion of energy in subregions. And this Dirichlet condition also is something that shows up a lot in holography, where the boundary values of your fields are sources in your CFT, whereas the conjugate variables here are something like your stress tensors. There's also an argument for this Dirichlet condition in terms of gluing subregions together. So if you wanted to kind of construct your space-time by gluing together two subregions, you have to come up with a way of sort of, well, yeah, understanding how you do the gluing right at the boundary. So in the Dirichlet form of the flux, what you do is you end up matching the intrinsic quantities. And so if you were doing a path integral, the metric is continuous in that case. Whereas if you were doing some sort of Neumann matching, where instead you wanted to match the momenta, you still get that the variational principle matches the intrinsic quantities, but the off-shell configurations now include things where the metric jumps at your surface, and that's quite a bit more singular than just having a jump in the extrinsic curvature. So that's if you're familiar with things like the Israel junction conditions, this situation here would be sort of allowing for something like distributional stress energy, whereas this Neumann thing is just a much more singular configuration. Okay, so we argue that this Dirichlet condition is sort of the right one to look at. And so once you've done that, the thing that you're really interested in after you've constructed these charges is you would like to also understand the algebra that they satisfy. So in a phase space, this would be something like you just compute Poisson brackets of your charges. In the situation we're considering where we're allowing fluxes, so it's something like an open system, you have to be a bit more clever in terms of defining the algebra, but this work by Barnish and Trossard defines sort of an algebra, a set of brackets for these charges that are just defined sort of quasi-locally, but are changing in terms of flux. So this equation, I think you can read it as sort of a time-dependent Hamilton's equation, where you say the total time derivative of your Hamiltonian is given by a bracket. And if you move this to this side, you can think of this as this flux being the explicit time dependence of your Hamiltonian. So the important thing is that you can prove this charge representation theorem that the brackets of your Hamiltonians is equal to, it represents the algebra satisfied by these vector fields up to a central extension. And we showed in this work that this central extension is completely determined by the boundary term in your gravitational action. So it depends on the failure of this boundary term to be completely to transform covariantly under diffeomorphisms. So we have this nice explicit formula for the central extension, and we'll basically be able to apply that in the case of black holes to work out sort of the central extension in the algebra. And this is the thing that you end up using to compute the black hole entropy, is this extension. So the final piece of this construction is that you have to work out what all of these quantities are on a null surface if you want to apply this to a black hole, which we know the black hole horizon is a null surface in space-time. So to do this, you sort of just have to work out some of the intrinsic and extrinsic geometry of the surface. The extrinsic geometry is the thing that you're going to use to construct these conjugate momenta. So your intrinsic quantities are just the metric, the degenerate metric on your null surface, and your null generator, which is the null vector that's tangent to your surface. And then your extrinsic quantities are things like your extrinsic curvature. You have this Hadjichek 1 form, which is measuring things like the rotation of the horizon. And the final thing that ends up being super important is the inaffinity. So your null generator has to be a geodesic, since it's a null vector that is tangent to a hypersurface, but it need not be affinely parameterized. And this K here is the failure of that generator to be affinely parameterized. So once you do this, you can go ahead and work out explicitly what this decomposition is. And the important quantity that we're interested in here is this, this boundary term that you need to add to the gravitational action to get a well-defined variational principle. And so this K ends up appearing explicitly as that boundary term. And this eta is just like the volume form on the null surface. So this is the thing that you're integrating over the null surface. So you should think of this L as the null analog of the Gibbons-Hawking-York term, which is defined for, say, like a time-like boundary. And it's been identified, sort of, people have known about this type of term since fairly recently. But given this formula that we have for this central extension, knowing this term and specifically the coefficient out in front of it sort of entirely determines this central extension. So another interesting upshot is that these pi ij and pi I can be explicitly computed in terms of these quantities defined on a null surface. And they give this an interesting null boundary version of the Brown-York stress tensor. So if you're interested in some sort of notions for holography for null surfaces, these things are likely to play an interesting role there. Okay, so that's sort of the formal development of the quasi-local charges. From here, I'd like to move on to the specific application we have in mind, where you find some set of Virasoro charges and relate this to the black hole entropy. So this was motivated by this recent work by Hako, Hawking, Parry, and Strominger, where they found for the case of a Kerr black hole in 4D, there's a set of conformal symmetries you can write down. And they showed that this was related to the black hole entropy via one of these Hardy formula arguments. So one thing we wanted to do, we did in this work, was we showed that this construction works quite generally anytime you have an axisymmetric non-degenerate killing horizon. So this lets you apply these arguments to things like higher dimensional, like Myers-Perry black holes, or you could also apply it to things like cosmological horizons as well. So it gives a nice generalization. So the main features that you have sort of this vector chi, which is this horizon generating killing vector. So just to draw a picture of the horizon, you have, say, like your bifurcation surface of your black hole. You have this horizon generating killing vector that kind of generates, looks like a boost near the horizon. You have something like psi, which is like your rotational killing vector. Okay, so this one's the boost. And you can canonically define, using the gradient of your killing vector, this radial vector rho, which sort of looks like a dilatation near your bifurcation surface. Okay, and so using these three canonically defined vectors near your black hole horizon, you can show that the metric, you can write down a set of coordinates that puts the metric into sort of a Rindler form. So the metric ends up looking like Rindler times some transverse directions. So once you have this form, you can then define a set of conformal coordinates, which are given by this following coordinate transformation. What these depend on is this kappa, which is like the surface gravity of your black hole horizon, and two parameters, alpha and beta, which are going to be related to notions of temperatures in the CFT. And when the point of this coordinate transformation is to make the new horizon metric look like it has an ADS3 factor. So right here, the T, phi, and R coordinates can be rearranged to look like an ADS3 factor. And the reason this is useful is that in ADS3, we know sort of how to, there's this standard result by Brown and Hanot that you can get a central charge for the asymptotic symmetries of ADS3, and this then Strominger showed that the central charge is then related to the entropy of, say, BTZ black holes. So we can do a similar story here where we look at the symmetries of this ADS3 factor in order to construct a set of, of Virasoro generators acting near the horizon. So these Virasoro generators, you just write down what are the generators that preserve this ADS3 factor. They satisfy this centerless Virasoro algebra. And so one of the neat things to realize is that the zero modes are sort of these linear combinations of your boost and rotational killing vector. So the difference of the zero modes is just your angular momentum generator. And so this is just like your L0 minus L0 bar gives you the rotation generator in a CFT. And then your boost generator here is this specific combination of the zero mode generators. And so this relation is important because it allows you to identify this notion of left and right temperatures in the system. So just as kappa is sort of related to the Hawking temperature of your black hole, these alpha and beta end up being related to these left and right temperatures, which are sort of your potentials thermodynamically conjugate to the charges associated with these two helical killing vectors, C0 and C0 bar. Okay, so once you have your ADS, well, your Virasoro generators, and you've identified your temperatures, you essentially have everything in place to try to compute the charges and the algebra and relate it to the black hole entropy. So we have this general formula once you've constructed your charges for the extension and you can just immediately apply this to the generators that we've defined. And you see that this diff S1 algebra ends up getting centrally extended to 2 copies of Virasoro. And this is characterized by 2 central charges, C and C bar, which are equal and related to the area of the black hole via this formula. So once you have these quantities, you can go ahead and apply this Cardy formula, which again just gives you the density of states. So in this case, this is giving you the entropy in a thermal state of a CFT at these 2 temperatures, T and T bar. And so when you work this out, you find that the entropy you get is twice the Bekenstein-Hawking entropy. So it's twice the area over 4G. So this actually posed a bit of a puzzle for us for how to interpret this result that you get this entropy that's twice the black hole entropy. And there's sort of 2 possible explanations for this fact. The first that's kind of compelling, I think, is that we're working with this Barnish-Tressar bracket, which we had to use because we were dealing with sort of an open system where you're exchanging fluxes with some complementary region. And that sort of suggests that really this construction requires a complementary region to kind of collect the flux that you're losing. And so we developed this picture where it could be that this bracket is really sensitive to sort of both sets, both the subregion you're dealing with and the complementary region. And so it's essentially, you would say the complementary region should just be a copy of, so if the boundary charges here are telling you that there's sort of a CFT living on the horizon, the complementary region that you want to glue on to construct the global spacetime should also have a copy of that CFT. And this picture in terms of edge modes is that you should entangle these 2 CFTs to sort of build up the interior geometry. So if this is what was going on and this bracket was kind of computing the central charge of both CFTs, this thermal Cardy calculation would of course give you twice the entropy because you just have 2 copies of the system. And then if you maybe trace out one of the sides, you would end up with just half that entropy. So if you just wanted the entropy on one side, you would then reduce the factor of 2, and then you arrive at the black hole entropy. So in order to check this conjecture, you would have to kind of carry out this gluing procedure in more detail, but I think it's an interesting concept that this algebra might be sensitive sort of to the complementary region as well. Another argument that we had that was sort of in favor of this was that we said, okay, instead of working with this open system, is there a way for you to impose boundary conditions so that you can just view one side of the horizon as a closed system? And we found that this was possible, but in order to do this, you needed to use boundary conditions that aren't Dirichlet. So if you recall the the central player was this kind of L contribution, which is this boundary term in your action. And for Dirichlet, it had a very specific coefficient, but we found that those conditions don't actually lead to sort of integrable generators, so you don't get a closed system. But if you did want to instead construct a closed system, you would essentially have to use half the value of the Dirichlet boundary term. Furthermore, we showed that the temperatures had to satisfy this very specific relation where their difference is controlled by the horizon angular momentum divided by the area. And so in this case, you get the central charges are cut in half. So if you applied the same argument, you would get, again, just A over 4G. And in this case, it's also, you could do a little bit better because you can actually get this microcanonical Carty formula to work. Roughly, the idea is that since we are now dealing with a closed system, the canonical entropy and the canonical and microcanonical ensembles should essentially agree. And so you can use this alternative formula and you see it agrees and gives you the black hole entropy. So this gives a nice picture where you have this sort of CFT living on your horizon, and you sort of have some description of microstates in terms of the symmetries of that CFT and the states in the CFT. So to conclude, I wanted to maybe mention this recent work on a set of what I called surface preserving charges that also gives another interesting class of observables on more generic surfaces. So the idea is these fluxes we were considering so far, or these charges we were considering so far, are sort of associated with sort of translations that are moving you sort of forward in time or forward along a null surface. And so they're kind of naturally associated with an energy. But you can also just consider transformations that are instead that preserve your surface. And the presence of your surface still is breaking the Diffie symmetries. And so there's non-trivial charges associated with these transformations as well. So this work by Donnelly and Friedel in 2016 sort of identified this, a set of symmetries that are acting in this case. And I've done some work generalizing this to higher curvature gravity theories. But you end up with a symmetry group that's diffeomorphisms of basically all diffeomorphisms of the surface that you're considering. So those are things that where the diffeo looks like it's parallel to the surface at the surface. And you can think of those as sort of generalizing this infinite dimensional generalization of angular momentum for your surface. So you get, if you had an axisymmetric situation, the rotation generator is one of these diffeomorphisms, and you would end up writing down the angular momentum of the surface. So there's just an infinite dimensional set of charges in general relativity that generalizes that. The other types of surface preserving transformations are the ones that just vanish at the surface, but they sort of look like a boost near the surface. So in general, you get an SL2R algebra, and the charges associated with that are something like the local area element. So in order to, so this it was a nice construction. You can identify these charges, and sort of the relevance in, say, a quantum theory is you would like to understand how to quantize that algebra and maybe carry out this gluing procedure. And so the quantization involves studying representations of this symmetry algebras. So one of the things we did recently was we wanted to sort of initiate the question of how to understand the representations of this algebra. And one of the technical tools you can use that is this construction of coadjoint orbits, which generally are related, have a very intimate relation to the representations of the algebra. And so what we wanted to do was classify these coadjoint orbits, and there's a nice analogy that we made between this symmetry group associated with the surface and a more familiar case, which was the Poincaré group and its representations. So both of the groups have the structure of this semi-direct product. And if you're familiar with the classification of Poincaré representations, you start by writing down this first Casimir that's just the total mass, say, of a particle. So it's the invariant mass constructed from the momentum. And we showed that the analogous object in this case is the area of the surface. It's essentially coming from integrating the Casimir for this SL2R factor. The next step is you consider sort of the little group, which is going to tell you something about the spin of the particle in the case of Poincaré. So if you have a time-like momentum, that's just the group of rotations. The analogous object here is the group of area-preserving diffeomorphisms of this two surface in space-time. The generator of the little group in the case of Poincaré is this Pauli-Lubansky vector. It just generates rotations that fix a given momentum. And so this was kind of the interesting thing, that the analogous object was this curvature invariant that's defined for a codimension 2 surface, which is known as this outer curvature. It's essentially if you have a codimension 2 surface, so there's two normal directions, and if you try to parallel transport the normal directions on your surface, there's a non-trivial connection associated with that, and you get a curvature of that normal connection. And that's this quantity here. And you can relate it to the space-time Riemann tensor and the extrinsic curvature of your surface. So the final thing to do is to sort of characterize the Casimirs associated with the little group. In the case of Poincaré, you get this, just the spin of the particle. And so in the case of our symmetry group, there's this infinite sequence of what we call generalized entrophies, where we take the moments. So this is a curvature defined on the surface. It can be characterized just in terms of a function, and you take the moments of those entrophies. And so these entrophies are now things that characterize sort of what representation of area preserving diffeos you're working with. So I just wanted to mention that these entrophies are also a really interesting set of observables, say in 4-dimensional spacetimes associated with two surfaces that kind of generalize. So not only do you have the area of the surface, but you have some sort of infinite sequence of entrophies that characterize the type of surface you're dealing with. Okay, so just to maybe summarize the ideas I've been presenting here, I wanted to talk a bit about quasi-local charges in general relativity. And in order to do that, you use this Wald-Zupas procedure to define notions of charges. And in the case of black holes, you can construct a set of charges associated with a Virasoro symmetry algebra. And if you use the Carty formula in this case, you can show that this Carty formula for a CFT with the same central charges as you computed using the gravitational variables ends up giving you the entropy of the black hole. And so this sort of hints at a holographic description of the microstates of the black hole. And finally, I mentioned these additional charges that are associated with more general surfaces and showed there's sort of this infinite set of invariants associated with that charges. So not only do you have the area, but a set of moments of this outer curvature that define an interesting set of observables and would be really relevant for understanding quantization of this algebra. And some future works that I've been considering is there's definitely some applications of this Wald-Zupas procedure to asymptotic symmetries. So people who are interested in asymptotically flat spaces, for example, there's some interesting ways to think about charges defined at null infinity using this Wald-Zupas procedure. So that's some ongoing work I've been thinking about. There's certainly applications for this idea of subsystems in gravity and how to think about these page curve calculations, the more general problem of factorizing the Hilbert space in quantum GR. And there's more to be done understanding these representations of these surface symmetries and thinking about these Casimir invariants. Okay, so yeah, I guess that's basically all I wanted to say, so I can go ahead and conclude and welcome any questions. So thanks.
Thank you. Thanks, Antony. So yeah, we have time for questions. Please raise your hand or unmute yourself and ask. Maybe I can kick this off. So I actually have a question about the second point in your summary here. I didn't understand during the talk. It seemed to me that that the Virasaurs you were talking about would arise for any Killing horizon, not just a black hole horizon. So we could be talking about a Rindler horizon in flat space. Is that right? And if that's the case, then perhaps it's not so surprising that the entropy came out to be twice black hole entropy, because I would think that if you go through the entire calculation and it remains unchanged on a Rindler horizon in flat space, I shouldn't be computing any entropy. So in that case, it would be strange if there was actually any non-trivial result. So yeah, can you explain the second point? Where exactly is it important that you apply, that you get the Virasaurs if you apply this to black hole horizons rather than an arbitrary Killing horizon?
So, I mean, one of the things we wanted to do in this work was show that it does actually work for any Killing horizon. In the case of a Rindler horizon, the only thing that really goes wrong is that things are kind of IR divergent. It's just this formula right here is just infinity, because the area of your Rindler horizon is infinite in that case. You could imagine, though, kind of, since we're assuming that we have axis symmetry, in this case, it's sort of important in this setup that the orbits of your rotational vector are closed in order to essentially get this mode decomposition here. So in the case of a Rindler horizon, you might actually want to do an IR cutoff by kind of like periodically identifying along some IR scale. And once you did that, I think everything would now go through. You kind of have this IR cutoff, and so then this formula will now make sense. And you still get the factor of 2 in terms of that IR regulated horizon. But yeah, more generally, we did want to show that this general construction works for any Killing horizon. I mean, the original
entropy of what?
It's the entropy of a horizon. So for a Rindler horizon, there is a notion that you can define an entropy for that surface. It's sort of, I think just in general, in gravity in general, you think of surfaces in space-time as generically possessing entropy. One of the situations where this is defined for more general surfaces that aren't even Killing horizons is in holography, where you have this Ryutaki-Yanagi formula where, okay, the surface needs to be extremal, but otherwise you can get very generic surfaces in space-time, and you still get an entropy that at leading order is proportional to the area there. So I would say
in that case, you're computing the entanglement entropy of the boundary CFT that's right, dual to your gravitational theory. But for black holes, we also would like to imagine that we're computing the degrees of freedom that are making the black hole, basically, right?
Yes.
So that we want to think that there is a bulk notion of degrees of freedom that comprise this entropy, and you're counting that. So I'm curious, what would be your proposal for this kind of, arbitrary surface in the bulk and its entropy the entropy that it encloses. Or I'm curious, what would your conjecture be about what this entropy is counting in terms of bulk degrees of freedom if the surface is just arbitrary?
I mean,
Is it
usually,
just entanglement entropy between interior and exterior degrees of freedom?
yeah, that's
what you would
usually
say?
how to think about that. I mean, there's a very deep connection between entanglement entropy and the Bekenstein-Hawking entropy. Actually, when you're talking about entropy for black holes, you usually start talking about generalized entropy, where maybe just to write some formulas, the generalized entropy, right, is equal to A over 4G plus S, sort of the entanglement entropy of fields outside of the black hole. And there's this really nice story where, you know, you can move entropy between these two terms just by changing your cutoff in the theory. And in general, even like in holography, if you have your ADS black hole and you think about what the CFT description is, you really are computing an entanglement entropy between sort of the two CFTs living on the two asymptotic boundaries. So that's just to motivate that entanglement entropy is sort of deeply tied to this black hole entropy. And the way I think about what's going on for this is that the microstates that you're putting here on the horizon, I really do think of it in terms of this entanglement between kind of edge mode degrees of freedom. So the idea is that you kind of have to stick a CFT at the boundary of your space-time, or sorry, at the bifurcation surface in order to split your gravitational theory into two subregions. And what you want to do is then entangle the two CFTs that you stuck there in order to build up to kind of glue the space-time back together. So I would say that it's some notion of a CFT defined on the finite surface here. And there's lots of interesting developments recently for how to define, these notions of holography for sort of finite cutoff surfaces. And so I would imagine that it's something like that. Beyond that, though, there's nothing, I don't think you can get much more microscopic information from these general symmetry arguments, just because, I don't know, the gravity theory probably doesn't know everything about the UV completion. So it's motivating that there ought to be some bulk CFT description of degrees of freedom living at the horizon, but it doesn't say much more than that. So yeah, hopefully that answers a bit.
Yeah. Any other questions? I'm actually curious about something else. So at some point you mentioned, you made an analogy. You said we could think about the boundary fluxes in terms of Israel conditions. It's a technical question, but if I actually impose both intrinsic and extrinsic curvature for a smooth transition, so no distributional stress energy tensor, both Israel junction conditions, would that mean that I would get 0 charges? Is that what you would say?
No. The charges, so yeah, let me see if I can show you this formula again. So the matching condition ends up just saying it's sort of which variables you end up matching kind of kinematically versus which ones you match dynamically. So this argument here was, if I write down the Dirichlet condition, what I'm really talking about is I'm going to kinematically match the induced metric, and then I can use the variational principle for the subregion and its complement to show that kind of on shell you get the second matching condition for the jump in the extrinsic curvature, basically, something like that.
Right, but Israel would say that for a smooth geometry, you'd have to match also, set those equal as well.
Right.
The extrinsic curvature.
And so I'm just saying that ends up matching dynamically. it's just that if you were considering off-shell configurations, you're sort of allowing for jumps there. So, but it's just the form of the flux then for that type of setup is that you have to have this flux be of Dirichlet form. And that just determines kind of what which boundary term you add to your action when you're doing this variational principle. And the way that affects things is it just affects this additional contribution to the charges. So they're not zero. So, you know, you could pick something where you just say you want L to be 0. You would still get charges coming from essentially this Komar type term. But we were arguing that it's probably better motivated from a path integral perspective to think about this Dirichlet matching. Just because if you're integrating over off-shell configurations where the metric jumps, it's just a more singular thing than having jumps in your extrinsic curvature.
Right. But on shell, you're saying, you know, you would get.
On shell, you end up matching both.
Yeah.
It's just sort of which one is you know, imposed. Essentially, for the Dirichlet, we're saying the off-shell configurations also match the metric, whereas the Neumann conditions, you're allowing off-shell conditions where you don't match the metric, but you match the
good
stress tensor. Yeah.
All right. I don't see any raised hands. So I guess, yeah, it's about time. So I guess going once, going twice. Okay, so let's thank Antony. Thank you. Thanks a lot for a very nice talk. And we'll see everybody next week. Bye-bye.
Thank you.